great thing about graphing a sine function, or graphing any trig function for that matter, is that trig functions are periodic. We conceptually build trig functions based on relationships around the unit circle, so instead of a particular y value repeating at most a couple of times, if at all, and then exhibiting some sort of final end behavior as we progress through a function's domain, like we saw with algebraic or exponential functions, these y values occur over and over as the x value increases and we keep looping around. So our graph will be cyclical. When we graph a sine function, the input, or x value, is the degree measure of the particular angle, and here we'll be using radians pretty often, and the output, the y, is the corresponding sine value for that angle. For the essential y equals sine of x, sine of 0 is 0, sine of pi over 2, or about 1.57, is 1, sine of pi is back to 0, sine of 3 pi over 2 is negative 1, sine of 2 pi is 0 again, 5 pi over 2 is back up to 1, and so on. We can also backtrack and go from, say, 0, 0 to negative pi over 2 and negative 1. Cosine is identical, again with that quarter turn shift. Quick advisory, you don't have to unreel a whole bunch of cycles on a graph, but it is proper form to include at least one complete cycle, preferably with a bit of a margin on either end. This new form brings with it a few new transformations to consider and potentially use. Standard form of a sine function is y equals a times sine of bx minus c plus d. So when we set up the equation, there are actually now 4 different variables that must be considered and implemented. 2 of these actions are familiar. C is the horizontal translation, which we now call a phase shift, and moves the graph to the left or right in the frame. D is a vertical displacement. It shifts the entire graph up or down. Up until now, dilation has been something of an afterthought, especially in graphing. The equivalent of dilation here, amplitude, is perhaps more significant in usage and certainly much more visible. Amplitude changes the height that each cycle reaches. A is half the distance between the high point and the low point. We can also have negative values for A, which mirrors the graph along its central axis. B is a new one for us. B defines the period of the function, the space between 2 matching points or a complete lap of the unit circle. If we're measuring in radians, a normal period is 2 pi. If we multiply x by a certain factor greater than 1, we can speed up its trip around the unit circle, effectively shortening the period. If we multiply x by a fraction or divide it by an integer, we slow down the trip and stretch out the period. For example, multiplying x by 2 gives us 2 complete cycles in a 2 pi frame. Side note, a b of 2 pi gives us a period of 1, so we can easily manipulate that to our liking. Let's set up an entire equation transformation by transformation. Say that y equals 2 sine 3x plus pi plus 1. Let's go a, b, c, d. Start with the standard sine wave. Amplitude is 2, so we have the peaks crest at 2 and the valleys bottom out at negative 2. B is 3. We get 3 complete cycles in our standard 2 pi framework. C adds pi to the position on the unit circle. We move the whole graph, as we've drawn it so far, to the left by 3.1415 and the rest. And D shifts it all up 1 unit on the y-axis. B will be consistently the trickiest for us to sort out, but the rest should be rather intuitive even at this point.